It started as a subtle anomaly, the kind most datasets would overlook. A curve, slight, smooth, and almost too elegant to be accidental, began appearing in the orbital models of 3I Atlas. Not a deviation from chaos, not the jagged tug of solar radiation pressure, nor the spinning lurch of asymmetric outgassing. This wasn't instability, it was the opposite. It was precision, and that's what made it so concerning. In the early morning hours of December 28th, analysts inside JPL's Near-Earth Object Program gathered around fresh outputs from their latest orbital simulations. Overnight, a small adjustment had been made to the trajectory modelling software. Just a minor calibration in how solar drag was being calculated, but the result wasn't minor. It revealed a consistent repeating arc in the object's motion. Not random, not reactive, a bend, a deliberate-looking turn. At first, it seemed like noise. Instruments can be imperfect, and interstellar objects often create modelling headaches. But as the update propagated across partner observatories in Europe and South America, a consensus quietly began to form. This wasn't a blip, it was a signature, and that signature had a shape. The curve didn't match any known pattern of non-gravitational acceleration. It wasn't the result of a jet firing off from an ice pocket. There was no torque, no wobble, just a smooth radial drift, a refinement of motion, not a distortion of it. Like a spacecraft adjusting mid-flight, as though it had received a silent command. The most striking part wasn't just the presence of the curve, it was when it began. Data logs from 2 days prior, December 26th, show that the object's motion was still within expected bounds, and then, at precisely 0433 UTC, the shift began. The path bent. Not sharply, not even dramatically, but measurably. The object was no longer on its straight outbound hyperbolic path. It was banking, just slightly, just enough. To the naked eye, nothing changed. No new tail, no light burst, no disintegration. But the models told a different story. The orbital solution, the predictive path calculated by multiple agencies, began to diverge from reality by a small but growing margin. And in astrodynamics, even a few hundred kilometers over a week becomes meaningful, especially when that margin appears not to be the result of chaos, but of intent. It wasn't long before someone noticed what lay ahead, along that new curve. The updated vector wasn't random. It was falling into alignment with a corridor long used by spacecraft seeking gravity assists, the edge of Jupiter's magnetospheric bow shock. Not the planet itself, but the space around it. A vast domain where magnetic fields stretch into interplanetary space like invisible tendrils. This is where things change direction. Could 3I Atlas be aiming for that? And if so, why? Historically, no comet, interstellar or otherwise, has ever been observed navigating with this level of accuracy. They are subject to luck, not logic. Their paths are ruled by the chaotic breakdown of ices, by heat, by mass loss, and by spin. But this wasn't spin. This wasn't decay. This was something else. Multiple orbital analysts hesitated to comment on the record, but the phrasing in internal memos became careful. One read, "Object exhibits persistent deviation from projected inertial trajectory, magnitude within acceptable bounds, directional alignment under review." That's coded language. It means the object is moving in a way we can't explain. Not yet. By noon, ESA's Deep Space Antenna in Tibreros had confirmed the same trend. So did Canada's CFHT array. 3 systems, 3 independent confirmations, and 1 curving line on the map that no one could deny anymore. The question wasn't whether 3I Atlas had changed its course. The question was what it had just aimed for. When the curve was first detected in 3I Atlas's outbound path, most eyes turned to its changing motion. But while trajectory analysts focused on orbital vectors, another team noticed something just as strange, though less visible. It was a drop, not in brightness, not in spin, but in thermal output. The discovery came not from Earth, but from orbit. On December 27th, ESA's solar orbiter passed through a clean telemetry window. Its onboard thermal images, designed primarily to monitor solar plasma and ejecta, happened to sweep across the zone containing 3 Atlas's projected location. Embedded in that data was a faint but undeniable pattern. a moment of cooling, a symmetrical dip in temperature that lasted only 8 minutes, and then returned to baseline. To the average observer, this wouldn't register as strange. In deep space, temperatures fluctuate all the time, but this wasn't fluctuation, it was precision. In the hours leading up to that thermal change, 3I Atlas had maintained a stable heat profile, consistent with reflected solar radiation, background cosmic microwave exposure, and its own low-level activity. And then, as if a switch was thrown, it cooled. The readings weren't dramatic, a slight decrease in infrared emissions, a lowering of thermal glow in the 10-15 micron range. But what made it significant was timing. The dip occurred exactly 19 minutes after the object's curve began, the orbital turn that pointed it toward the Jupiter corridor. Cooling usually follows a change in exposure, like if a rotating object shifts its sunlit face. But the spin rate of 3I Atlas derived from brightness variation data hadn't changed, and neither had its distance from the Sun. So if this wasn't caused by sunlight, what was it? Some suggested shadowing, a natural depression or ridge on the comet's surface momentarily shielding part of the nucleus. But that explanation collapsed when the thermal drop showed up again 6 hours later, nearly identical in duration and depth, a repeat dip, same zone, same profile, and then silence. What was seen wasn't just a loss of heat, it was a controlled reduction in emission, a momentary suppression like a cooling system cycling on. This raised new questions, ones that drifted from the margins of cometary science into the territory of thermal regulation. Could a natural object self-moderate heat this way? There are some natural materials, amorphous carbons, layered silicates, certain exotic volatiles, that can temporarily store energy before releasing it as heat. But not with this kind of consistency, and certainly not with this timing. At NASA's Jet Propulsion Laboratory, analysts modelling the comet's energy budget found that the amount of thermal energy missing during the dip lined up with the energy required for a mild course correction, if converted with even modest efficiency. That's when a hypothesis began forming. What if the heat wasn't lost, but used? If 3I Atlas is expelling mass, even microscopically, that mass requires energy to be accelerated. And in the vacuum of space, heat is a form of stored energy. If the object absorbed enough solar radiation during its earlier close approach, it may now be drawing from that internal store to make adjustments. Not by accident, but by choice. And suddenly, a thermal dip becomes more than just a drop. It becomes intent. It becomes engineering. The anomaly passed, the object warmed again, and its curve continued, now accompanied by a second mystery, one that didn't burn bright, but faded cold. Every object in space moves, but how it moves tells the story, and in the case of 3I Atlas, that story just became harder to explain. Acceleration in space is almost always the result of one of three things: gravity, radiation pressure, or outgassing. For most comets, it's the last one. As solar heat vaporizes subsurface ices, they burst outward in jets, pushing the nucleus in the opposite direction, like weak, erratic thrusters. These thrusts are chaotic, messy, asymmetric. They wobble the comet. They change its spin. They produce irregular forces. But on the night of December 27th, 3I Atlas broke that pattern entirely. Observatories across 4 continents, Hawaii, Chile, South Africa, and Spain, all reported identical movement. The object's velocity had increased, its vector had shifted, but the change was smooth, linear, rhythmic, not erratic, not noisy, not random. The acceleration followed a sigmoid curve, a classic S shape. It began slowly, ramped up gently, reached a plateau and then stabilized. It wasn't a burst, it wasn't a spin, it was measured. If plotted on a graph, the profile wouldn't look like a natural venting event. It would look like a thrust burn. This shouldn't be possible. Comets don't accelerate like this. Even 2 Borisov and 1 Oumuamua, the 2 prior interstellar visitors, showed signs of chaotic motion during their most active phases. But 3 Atlas, even while shedding mass, was accelerating with a kind of grace. It didn't twist. It didn't tumble. It simply adjusted course like it had a mission. When the Pan-STARRS array recalculated the force vector, it found that the direction of acceleration was almost perfectly radial. pushing the object away from the sun along a clean line. But the sun was already behind it. This wasn't sunlight pressure anymore, and it wasn't aligned with any known jet previously observed on the object. That left only two explanations. One, the object was experiencing a non-gravitational force from an unknown mechanism. Two, it was generating the force itself. Some tried to model this as a venting event. If a buried ice pocket had ruptured and vented in one direction, maybe the force could look this clean. But when spectroscopic data came in from Chile, it showed no increase in gas release. No signs of violent sublimation, just steady-state emissions. In other words, nothing had changed on the surface, but the object had started moving faster. Then came the telemetry from radio arrays in South Africa. As the object accelerated, a momentary drop in received signal strength was observed, followed by a return to normal. Not interference, not atmospheric noise, just a sharp, brief reduction in radio reflectivity, as though the object had turned, as though it had angled itself. That's when everything aligned. Thermal dip, curve in path, acceleration pattern, and now directional reflectivity change, all within the same 12-hour window. That's not noise, that's a maneuver. It's no longer a question of whether 3i Atlas is accelerating. It is. The question now is, what is it accelerating toward? And, perhaps more disturbingly, who or what told it to? At first, it seemed like coincidence. The curve in 3i Atlas's trajectory was undeniable, but where it was leading, that was harder to confirm. Celestial paths are complex and with hundreds of gravitational influences pulling at every interstellar object, predicting a long-range course isn't always conclusive. But when the new orbital solution from JPL landed in astronomers' inboxes on the morning of December 28th, the coincidence became something else entirely. The object wasn't veering randomly, it was targeting a corridor that intersects with the outer edge of Jupiter's magnetic domain. This isn't empty space. It's one of the most structured regions in the solar system, a vast torus of plasma, radiation and magnetic field lines. Invisible, but not inert. The place where Jupiter's gravitational influence begins to shape charged particles into motion. This is where spacecraft go to change direction, to gain speed, to steal momentum from a giant without expending fuel. And 3i Atlas is headed straight for it. The vector is now less than 0.02 degrees off from the midpoint of the Jupiter-Sun Lagrangian line, a stable corridor used in theoretical mission planning for decades. It's a place of dynamic balance, where gravitational and centrifugal forces cancel just long enough for an object to pass cleanly through. It's not a place a comet would ever intentionally aim for. Unless it's not just a comet. No natural outgassing or sublimation model explains the correction path this clean. The math says the object began accelerating not away from the sun, not toward any particular planet, but toward a window. A region of space where momentum transfer is possible. The kind of transfer we've used with Voyager, with Galileo, and with the Parker Solar Probe, a gravity assist. To the untrained eye, it may look like any other orbital arc, but analysts specializing in deep navigation know the signs. The smoothness of the curve, the increasing match to the assist corridor, the velocity plateau that mirrors propulsion models used in interplanetary maneuvering. If this object continues on this track, and no new forces interfere, it will pass within a few 100,000 kilometers of Jupiter's magnetic bow shock. That's not a casual drift, that's a calculated entry. So now the question changes. Was this always the plan? Was Jupiter the real objective all along, not Earth? Some believe the initial approach vector was a ruse, a feint. Let Earth's instruments focus on its near pass, while it quietly aligned itself for something bigger, something deeper in the system, something with gravity strong enough to slingshot it out of the ecliptic and into another trajectory entirely. Or maybe Jupiter isn't the endgame. Maybe it's just another launch point. That's what makes this terrifyingly elegant, because if 3i Atlas is using Jupiter as a gravity well, as a thrust multiplier, it implies not only foresight, but mission planning. The last time a celestial object moved like this, it had solar panels. This one does not, at least not visibly. But the result is the same, a course correction that defies randomness, a vector that obeys no chaotic model, a plan written into the stars unfolding without words. It's no longer drifting, it's navigating, and it's heading to the one planet that rewrites momentum, Jupiter. By the time the new trajectory pointed toward Jupiter, astronomers were already rechecking everything near its path: moons, plasma fields, and magnetic anomalies. But it was something small, almost mist, that delivered the next surprise: a whisper, a signal, a flicker buried deep in telemetry from one of the least likely sources, Europa. The icy moon, long known for its fractured crust and hidden ocean, is currently under continuous observation by ESA's JUICE mission, the Jupiter Icy Moons Explorer. On December 27th, at 11:06 UTC, its onboard magnetometer picked up a disturbance. Not a wave, not a pulse, a localized spike in flux density, a clean, narrow echo that shouldn't have been there. At first it was dismissed. The region Europa was in at the time was expected to show some turbulence. Jupiter's magnetic field is wildly complex and plasma noise isn't rare, but what caught the attention of researchers at the European Space Operations Centre wasn't the signal itself. It was the timing. Exactly 17 hours prior, 3SE Atlas had crossed the plane that connected its outbound arc to Europa's orbit. Not close in terms of kilometres, several million separated them, but close in terms of line of sight. And within the charged latticework of Jupiter's electromagnetic field, line of sight sometimes means something more. The anomaly wasn't strong, it wasn't dramatic, but it was clean, and it had no precursor. Just a single, narrow electromagnetic shift in the low kilohertz range, lasting less than half a second. It resembled a call and response, only the sender, in this case, wasn't known. Until now. Further analysis revealed something even stranger. The spike aligned with a phase angle between the Sun, 3I Atlas and Europa, forming what mission planners call a coherent transit corridor. It's used when aligning signal paths between spacecraft and moons through curved fields, and now it may have been used by something else. Could this have been an interaction? Not communication. There was no modulated content, but a response, an echo, the kind of electromagnetic disturbance that occurs when a moving object with high conductivity passes through a resonant field. Think of a tuning fork struck silently. Now think of Europa's icy shell ringing back. Some scientists at ESA proposed an alternative explanation. The flux spike was a reaction to solar turbulence, but solar conditions were quiet during the event. And there were no corresponding fluctuations in Ganymede, Callisto, or Jupiter's own ring zone. Only Europa, and only once, which raises an unnerving possibility. Was this a probe, using Europa's subsurface magnetic structures as a navigational relay? Or was the moon merely in the path, collateral resonance in a wider energetic system? The deeper fear is one of intent. Because if the object passed millions of kilometers from Europa and still managed to produce a field echo, it implies not only mass, but activity. That would mean 3I Atlas isn't just absorbing energy, it's emitting it. The scientists are cautious. The data is still being reviewed. But one quiet line in the internal memo from the JUICE analysis team says what many are thinking. Interaction unlikely to be environmental. Resonant alignment suggests deliberate phase timing. A phrase like that doesn't appear lightly, and just like that, Europa may no longer be just a moon. It may have just echoed back. In space, nothing stays still, but even the chaos follows patterns, especially when it comes to comets and their tails. For centuries, astronomers have relied on a basic truth. Comet tails always point away from the Sun. It's not artistic license, it's physics. The ionized gases released from a comet's surface are caught in the stream of solar wind, a relentless flow of charged particles erupting from the Sun at nearly 1 million miles per hour. The tail is more than just a visual byproduct, it's a compass. It shows direction, pressure, influence. Which is why what happened to 3I Atlas in the early hours of December the 28th shocked the analysts monitoring its behaviour. The ion tail moved, not just twitched, not just rippled, but shifted. A clean, measurable drift. And it didn't follow the direction of the solar wind anymore. For nearly 3 weeks, its ion tail had followed expected behaviour. Slight oscillations, some angular variations depending on where in the heliosphere it was travelling, but nothing that broke the model. But now the tail wasn't pointing away from the Sun. It was deflecting slightly, curving downward in the ecliptic plane, angling toward the direction of Jupiter's magnetosphere. It was subtle, only a few degrees at first, the kind of change that might escape casual telescopic observation, but to a seasoned heliophysicist, it was a red flag. Solar wind doesn't change direction easily, and certainly not at a localized level. For the tail of a moving object to change angle independently, something else must be at play. The team at the Solar and Heliospheric Observatory, SOHO, initially assumed a solar wind anomaly. Maybe a coronal hole had opened, altering the local flow. But the solar data didn't match. No change in particle velocity, no shift in field orientation. Then came the polar data from the Parker Solar Probe. It had been flying through a region just a few degrees above the plane of 3I Atlas. Its instruments confirmed what ground-based astronomers feared. The solar wind was steady. The field lines were undisturbed. The tail drift wasn't coming from the sun. It was coming from the object itself. One hypothesis emerged, and it wasn't a comfortable one. What if the shift in the tail was not a response but a side effect? What if 3I Atlas was generating a local magnetic disturbance, a field bubble, that was partially deflecting the charged particles around it? That would require energy. Not a lot, but more than any natural comet is known to produce, and it would require structure. Field generation isn't something dust clouds do. It's something coils do, or plates, or high conductivity alloys under current. A comet, in the traditional sense, cannot produce a localized field strong enough to alter the orientation of its own tail. But this one did. More models followed. The leading explanation from a subset of researchers was that 3I Atlas may be interacting with the heliospheric current sheet, the massive, wavy surface of the sun's magnetic field that flows outward like a warped sheet of paper. But even that model failed to explain why no other objects in similar positions had shown the same behavior. In the updated SOHO dataset, the deflection held for nearly 11 hours before slowly realigning, almost as if the disturbance had been turned off. Turned off. That's the phrasing that appeared, quietly, in the latest memos circulated among partner observatories. Something changed the behavior of 3I Atlas's tail. Not the sun, not a flare, not a solar storm, something on board, or something active. Because when comets drift, they leave trails. But this time, the trail moved first. In the vastness of space, shape is everything. When astronomers study comets, they rarely see the core itself. Instead, they observe the coma, a glowing cloud of gas and dust that envelops the nucleus, often thousands of kilometers wide. It's the result of sunlight vaporizing frozen volatiles from the comet's surface, turning solid into gas and dragging dust with it. Most comas are messy, chaotic, irregular. They expand in uneven pulses shaped by surface composition, temperature fluctuations, and outgassing events. Like smoke from a candle in zero gravity, beautiful but turbulent. But as 3I Atlas arced toward the Jupiter vector, its coma changed. The first reports came from Chile. The VLT, Very Large Telescope, had been observing the object intermittently over the previous week. In its latest composite, the coma was smaller, not fainter, tighter. The emissions weren't spreading outward in a chaotic bloom. They were narrowing, streamlining into a halo that looked structured. The initial assumption was distance. Maybe the object had simply moved far enough that the coma appeared smaller due to angle and resolution. But secondary observations from Hawaii and the Canary Islands contradicted that. The readings were adjusted for distance, and the narrowing persisted. In fact, the shape was more uniform at closer range, not less. That's not natural. Natural comas become less defined as objects move farther from the sun. Outgassing decreases, dust disperses, but 3 Atlas wasn't just holding its coma shape, it was refining it. High-resolution filters revealed a symmetrical bow-shaped forward edge, like an aerodynamic shell forming around the core. Behind it, the glow tapered smoothly, as if resistance, even in vacuum, had been minimized. There's no known mechanism in comet physics that could cause this. You can't tighten a coma unless you change how material is being released, or control it. If 3I Atlas had reduced its outgassing, the coma would shrink but also dim. That didn't happen. The brightness remained constant, so either the same amount of energy was being released, or it was being shaped. The shape alone tells a story. Comas don't form streamlined edges unless there's directional pressure, or unless the emissions are being collimated like exhaust through a nozzle. Some models from the astrophysics team at UCLA explored exotic sublimation geometries. Maybe there was a ridge or trench channeling the material in one direction. Maybe the nucleus had cracked into a symmetrical form by chance. But statistical models showed the odds of that happening naturally were less than 1 in a million. And there's more. The coma's reflectivity also changed. Spectrographic analysis revealed a shift in the polarization angle, meaning the dust particles weren't just changing position, they were aligning. In space, that kind of alignment requires either an electromagnetic field or an active shaping mechanism. In other words, someone, or something, was arranging the flow. Some compared it to the plasma nozzles on ion drives. Others saw echoes of magnetic containment fields used in experimental propulsion. But one thing was clear. This wasn't a debris cloud anymore. It was a form, a shell, a sheath of luminous gas shaped not by chaos but by order. 3I Atlas wasn't just getting cleaner, it was becoming something else. It was becoming aerodynamic, in a vacuum. That's not something nature does, that's something design does. On December 28th, a narrow band spike appeared in a part of the electromagnetic spectrum that usually whispers quietly from interstellar objects. It was faint, embedded in the data like a single unusual brushstroke in an otherwise consistent painting. But it didn't go unnoticed. The signal came from Chile's ALMA array, the Atacama Large Millimeter Sub-Millimeter Array, one of the most sensitive tools for detecting changes in infrared and microwave frequencies. ALMA had been monitoring 3I Atlas passively for over a week, capturing a continuous light curve across multiple wavelengths. Nothing unusual had been detected. Until now, at exactly 4:19 UTC, one of ALMA's receivers caught a spectral shift. Not a flare echo, and not cosmic background noise. It was a clean, momentary absorption feature in the mid-infrared band, something that hadn't been present in earlier datasets. The feature was centered near 14 microns, a region associated with vibrational modes of certain carbon-based molecules. But here's the strange part. Those lines had never been observed in 3I Atlas before, and they didn't correspond to carbon dioxide, which had previously dominated the object's volatile signature. Instead, the new lines suggested the presence of carbon-oxygen lattice bonds, the kind seen in carbonyl-rich compounds or partially polymerized organics. In other words, something was changing, chemically, on or near the object's surface. Spectral shifts like this don't usually happen quickly. They're the result of slow, cumulative changes, sublimation, heating, solar weathering. But this one was instant. One moment the signal was baseline, the next a spike, then gone. When ALMA's team reprocessed the raw data, the feature was still there. No artifact, no instrument glitch. Just a real, transient absorption band that passed like a shadow and vanished. To understand the implications, we have to remember what spectral fingerprints really are. Every molecule absorbs and emits light at specific frequencies. Those frequencies act like barcodes. They don't change unless the molecular environment changes, or the molecules themselves transform. So the question became simple. What just changed? Theories poured in. Some suggested this was the signature of surface processing, that sunlight had triggered a rapid phase transition in the object's carbon compounds. Others speculated that 3I Atlas may have ejected a shell of material containing different chemistry, possibly a deeper, older layer of the nucleus exposed after earlier heating events. But one theory was more troubling. What if the shift wasn't from passive heating, but from active rearrangement? In materials science, certain compounds can alter their structure when energy is applied, aligning molecules, forming temporary lattices, or even triggering microphase transitions. These behaviors are seen in smart materials, synthetic compounds engineered to respond to stimuli. If the object's surface or its emissions contain materials capable of changing reflectivity or composition in response to environment or command, then this wasn't a natural spectrum anymore. It was a modulated one. Some have pointed to the possibility of photoreactive compounds, substances that shift structure when struck by sunlight at a precise angle or intensity. But that theory falters under the timing. The event didn't happen at perihelion, it happened now, after the turn, after the curve, after the tail shifted, and that's what changes everything. The spectral fingerprint didn't just alter randomly, it altered in sync. A chemical change occurred at the same time as a trajectory shift, a tail drift, and a thermal dip. In the language of astrophysics, those alignments don't mean noise, they mean function, and in the language of engineering, they mean control. As of December 28th, the question is no longer theoretical. The path of 3 Atlas is now confirmed by multiple observatories and trajectory solutions. It's heading for Jupiter. Not directly into the planet's atmosphere, not even close enough to be captured by its gravity, but into a corridor that only a handful of spacecraft in history have passed through intentionally, the Slingshot Lane. This region isn't visible. It's not marked by rings or clouds or moons. It's defined purely by mathematics, a dynamic intersection of momentum, field strength, and relative motion. The exact zone where a fast-moving object can trade angle for speed or direction for energy by using Jupiter's enormous gravitational pull like a lever. It's a maneuver so precise that even the Galileo and Juno spacecraft, designed by some of the brightest engineers on Earth, required months of planning and correction burns to align for it. 3 Atlas is doing it without assistance, and the math is tightening. According to orbital analysis from ESA's Navigation Support Office, the object will intersect the edge of Jupiter's magnetosphere in approximately 47 hours. If current projections hold, it will pass just outside the Ganymede flux tube, a region of charged particles that connects the moon Ganymede to Jupiter's magnetic field. That area, by coincidence or not, happens to be a high-energy corridor where field lines are dense, acceleration is possible, and resonance effects can occur. If the object's goal is to gain velocity, this is where it will happen. But that's not the only possibility. Some scientists believe 3I Atlas is targeting this region not just for gravity but for power. In simulations, Jupiter's magnetic field can induce current in conductive objects passing through it. This isn't science fiction, it's physics. Faraday's law in motion. In fact, Ganymede itself emits a secondary field due to the effect. If 3I Atlas is constructed with a high conductivity surface, or internal materials that respond to field changes, it may be harvesting energy during this pass, not solar energy, magnetic energy. That possibility terrifies some researchers because it implies not just mobility, but adaptation. A comet doesn't use gravity assists. A fragment of interstellar ice doesn't care about flyby geometry, but this object is threading the corridor using both mass and magnetism, like it's done it before. As of now, its flyby path intersects 3 critical regions. 1, the outer Bow-Shock, where solar wind meets Jupiter's field. 2, the Ganymede flux corridor, dense with plasma resonance. 3, the L1 point of the Jupiter-Sun system, a region where velocity transfers cleanly. Each one is a checkpoint. Each one is a maneuver node. If this was a spacecraft, we would call this the critical burn window. Instead, we're watching a comet, or something that used to be one, and it's lining up a flyby with the precision of a mission. This isn't slingshot science, this is trajectory planning. And the solar system may not be the final destination. When the observational arrays began recording a deviation in 3I Atlas's projected path, the first instinct was to question the instruments. After all, comets of this size and velocity are notoriously difficult to model with perfect precision. Their tails, jets, and evolving mass distributions create minor variances all the time. But this was different. This was not a drift. This was not a natural wobble due to solar radiation pressure or gravitational tug. This was a clean angle shift. Subtle, yes, but far too precise to dismiss as coincidence. The shift was first confirmed by the ALMA Observatory in Chile, whose radio arrays had been tracking 3I Atlas's trajectory across several days. Compared to the plotted path used just hours earlier, 3I Atlas had adjusted its heading by a measurable arc-second. Not enough to alarm the general public, but just enough for the scientists watching it to sit up in their chairs and wonder how it happened. There was no sign of ejected mass, no visible outburst, no natural force that could explain such a focused maneuver. Solar winds had been mild. There were no nearby planetary bodies capable of gravitational slingshotting. And the object's rotational behavior, if anything, was settling, not destabilizing. And yet, it moved. To some, It brought flashbacks to Oumuamua's peculiar acceleration years ago. That too lacked a visible propulsion event. That too was marked down as a non-gravitational force, until it wasn't. With 3i Atlas, however, the evidence was arriving in real time. Instruments could no longer hide behind retrospective doubt. This was happening now under direct and constant observation. What remained most concerning wasn't just that the object had altered course, it was the destination implied by that new path. Instead of simply bypassing the Sun, in a slow spiral out, 3i Atlas now appeared to be curving back inward, slightly, gently, as if correcting a drift, as if it was realigning. Some speculated that the course change might have been in response to the magnetic behaviour detected days earlier, a kind of trajectory adaptation to solar field pressure. But that would require an onboard field detection mechanism, a level of sensitivity not typical of frozen rock and dust. What if it wasn't adapting to external forces? What if it was initiating its own manoeuvre? There was no fire trail, no venting gases, no emission spike, only a quiet, decisive redirection. And in that silence the question lingered. Who or what had made that decision? It happened during a rotation lull, when 3 Atlas's darker hemisphere turned once more into view. An amateur astronomer in Indonesia, equipped with a deep field telescope and filters calibrated for ultraviolet emission, recorded what appeared at first to be a camera artifact. A thin stream, brief, asymmetric, rising from the shadowed side of the object, arcing slightly into the vacuum. By the time larger observatories were notified, the phenomenon had ceased, but not before 3 other amateur skywatchers in different parts of the globe had confirmed the same event. A low, uneven jet, unannounced, unexpected. Unlike the earlier symmetrical jets near perihelion, this one was different. It did not originate from the heat-exposed face. It did not align with the expected subsolar points where frozen volatiles are most likely to sublimate. This one came from the dark side, cold, sheltered, quiet, and yet, for a few seconds, something breached its surface from within. Infrared replays from the European Space Agency's Gaia satellite later confirmed the presence of a heat signature in that precise location, one that hadn't existed hours prior. It was as if the surface had been pierced, as if something below had pushed through. Some speculated a pocket of gas, pressurized from earlier heating, might have tunneled its way upward and escaped through a crack in the crust. Others argued this theory didn't account for the lack of thermal build-up prior to the event. There had been no gradual rise. The jet arrived like a switch. On, off, done. It raised a deeper question. Why eject from that side? Was it accidental or intentional? Jets can alter spin. They can shift momentum. And on a body that just changed course without propulsion, the appearance of a jet on the opposite hemisphere begged for interpretation. If it was merely a geological event, it would have occurred on the side facing the Sun. But this was something else. A signal, a correction, a warning, we still don't know. But in the hours that followed, 3i Atlas's rotation changed ever so slightly, and once again we were forced to ask, are we witnessing the behaviour of a comet, or the programming of an object designed to behave like one? For months, every predictive model had assumed 3 Atlas would continue its elliptical escape, drifting steadily past Earth, then out toward the deeper edges of the solar system. But as the early light broke on December 28th, something changed. Telescopes in Hawaii and Chile independently recorded an adjustment in its vector, not a violent one, no explosive force, just a slight but unmistakable deflection. It wasn't the kind of shift a natural object makes. It wasn't like a rock being pushed by solar wind or gravity. This was deliberate, smooth, controlled, something you'd expect from a probe, not a comet. The vector shift was first noticed by a small team at the Atacama Cosmology Telescope. They had been calibrating instruments for unrelated cosmic background radiation readings when the object's new arc came into view. What they saw was startling. 3i Atlas was curving, not toward the Sun, not toward the Kuiper Belt, but sideways, cutting across a trajectory that intersected with several of the outer planets, then sharply adjusting toward deep heliocentric space. This wasn't just gravitational lensing, this wasn't just solar radiation pressure. The curvature didn't match those behaviours. It looked too smooth, too responsive. like it was reacting to something or heading toward something. As data poured in, the astrophysics community began working backwards. If the new path was intentional, what was the object targeting? Projections ran simulations, cross-reference magnetic flux lines, asteroid fields, exoplanet alignment windows. One conclusion emerged over and over again. 3I Atlas was heading toward a region that held no planets, no major gravitational wells, and no historical anomalies. But something about the new heading chilled the teams watching. It wasn't the destination. It was the way the object was getting there. Whatever had altered its trajectory was doing so with precision. No outgassing, no tail disruption, no heating. The comet's jets remained symmetrical. The anti-tail remained smooth. No sign of rotation bursts or chaotic tumbling that would indicate a random or destabilized course. That meant one thing. The change was internal. It didn't come from the Sun, or Earth, or Jupiter. It came from 3I Atlas itself. The question then flipped from where is it going to what made it change, and even deeper than that. Who or what is choosing its course? Back at NASA's Jet Propulsion Laboratory, several analysts pulled archived data from other interstellar visitors, Oumuamua in 2017 and Borisov in 2019. Both of those exhibited behavior slightly outside predicted models, but nothing like this. 3I Atlas had just redefined what foreign object meant. The new trajectory avoided gravitational wells, it sidestepped detection windows, it moved into a corridor of space with minimal solar interference. In short, it behaved like something avoiding being seen, like it knew what was around it. For the first time, agencies stopped talking about mass and velocity and started whispering about intention. The European Southern Observatory issued an advisory to all linked observatories to prioritize continuous tracking. But already, 3I Atlas was fading from optical range again. Its reflected spectrum dropped in brightness. Its energy signature narrowed. Its communications, if they ever existed, went silent. And still, it kept curving. It wasn't a comet anymore, not in the way we define comets. It was something else. A messenger, maybe. A scout. Or perhaps a survivor of something much older than we realize. But what no one expected was that this change would trigger something else entirely. Because just beyond the path it now took, a new shadow began to emerge. Not from space, but from history. From patterns once ignored. From data buried beneath decades of classified silence. And that shadow, what lay ahead on this path, would finally force even the most skeptical astronomers to admit what they'd resisted for years. 3I Atlas wasn't drifting anymore. It was moving with purpose. As 3I Atlas drifted deeper into its path beyond Earth, something peculiar began to emerge in its wake. It wasn't a visible streak like a tail of dust or gas. It wasn't the kind of ionized trail that comets often leave behind. Glowing under solar wind pressure, this was something else entirely. It was invisible to the naked eye, but for observatories tuned into the subtle magnetic fluctuations across interplanetary space, it was deafening. The instruments aboard ESA's Solar Orbiter and NASA's Parker Solar Probe began registering sharp, consistent disturbances in the heliospheric magnetic field. These weren't random pulses or artifacts. They formed a pattern, a wave-like distortion that undulated behind 3I Atlas as it travelled. Like ripples behind a ship, only this ship was warping the invisible threads of magnetism that connect the solar system together. At first, scientists debated whether this was a side effect of the object's composition. Perhaps the core contained highly conductive materials that interacted unusually with the solar magnetic field. That theory, while plausible, fell apart when one important detail emerged. The signature wasn't passive, it was active. Instead of merely reacting to the field it passed through, 3I Atlas seemed to modulate the field behind it. Magnetometers recorded pulses at regular intervals, too regular to be explained by natural turbulence. The ripples were rhythmically spaced, and most alarmingly they encoded reversals. Each wave carried an inverted magnetic polarity compared to the last. Like alternating electrical current, the trail oscillated. It created a kind of magnetic braid, woven behind the object. This kind of behavior isn't common in space, especially not on this scale. Magnetic reversals do happen naturally, but they occur across massive time spans or during solar cycles, not in moments, and not as part of a moving object's tail. So the question deepened. Was this trail a byproduct of 3i Atlas's internal mechanism, perhaps a rotating magnetic core, or was it doing something intentionally? Further out, instruments near Jupiter began detecting the same disturbance as the tail extended and spread. This wasn't a local event anymore. The braided field line pattern was expanding outward, distorting even the planetary magnetic signatures it passed through. Jupiter's own field, the strongest among the planets, began to show minor echoes of the disturbance. That's when comparisons were drawn to terrestrial experiments in magnetohydrodynamics, a field that studies how magnetic fields and conductive fluids interact. Some researchers noted eerie similarities between the patterns behind 3i Atlas and those found in plasma confinement systems on Earth, the kind used in early fusion reactor experiments. But no one was suggesting 3i Atlas was a fusion reactor, not directly. What they were suggesting was even more unsettling. Whatever this object is, it seems to understand the magnetic scaffolding of space. It knows how to thread itself through invisible pathways, using the solar system's own architecture to propagate patterns. And just like the alternating current that powers homes on Earth, this magnetic braid didn't appear random. The intervals between polarity reversals weren't chaotic. They matched specific ratios, a resonance pattern, a hum, something with internal timing. For planetary defense analysts, this development was deeply troubling, because a field this strong, even if invisible, could affect other objects. Satellites, spacecraft, radiation belts. In theory, even a planet's magnetosphere, if exposed too long, could experience fluctuations that affect everything from atmospheric shielding to radio communications. Yet the object kept moving, and the trail kept growing. As the team at the Deep Space Network continued to model the propagation path of this magnetic braid, another realization set in. The pattern was pointing somewhere, not just behind the object but forward. A corridor, a tunnel through the field lines. As if 3i Atlas wasn't just leaving behind a trail, or it was following one, or worse, mapping it for something that might follow. As 3i Atlas and the Swan object moved closer to Earth's gravitational sphere of influence, something unexpected began to unfold, not just in their paths, but in their very structures. Scientists monitoring both objects via NASA's Deep Space Network and the European Space Agency's Gaia instruments began reporting readings that pointed to a strange phenomenon, opposing tidal forces operating not between one object and Earth, but between the two objects themselves. This was unusual. Most tidal readings in space, outside of planets with moons, are straightforward. A large body exerts force on a smaller one, stretching or compressing its internal structure, often visible as subtle shifts in rotation or minor distortions in form. But what was being detected here didn't follow the usual pattern. Instead, 3i Atlas and the Swan object were seemingly responding to each other, as if locked in a gravitational handshake that tightened with each passing kilometre. Telemetry from ESA's Lagrange Point Observatory L1 showed micro-oscillations in 3i Atlas's outer layer, ripples that would normally be attributed to thermal gradients or solar pressure. But when matched against the Swan object's movements, a correlation emerged. Every time the Swan object adjusted position, even slightly, 3i Atlas showed a delayed but mirrored reaction. This wasn't coincidence. It was communication through force, tidal tension broadcasting between two celestial objects across millions of kilometers. The pressure maps revealed something deeper. As the two bodies drew near, each began showing signs of stress along their structural lines. In 3i Atlas, specific striations near the jet-emitting regions darkened and stretched. On the Swan object, the regions near its cometary sheath seemed to thin, like ice being pulled outward. Some scientists began speculating whether this was a kind of orbital contest, one object attempting to shift the other's course, not through propulsion, but by gradually distorting its balance using mass-induced tension. It was a theory that bordered on unprecedented. We've seen gravitational dances before, binary stars circling each other, moons pulled into synchronous orbits, even asteroids forming temporary duos. But never like this. Never with an interstellar object and an ancient low-activity comet entity coordinating movements in this way. It was as if they were aware of each other, not consciously perhaps, but mechanically entangled, each anticipating the other's next move in a slow, silent ballet. The broader implications grew unsettling. If these forces could be so finely balanced between two objects with limited visible propulsion, what else could they affect? Earth's gravity, while dominant in our immediate vicinity, was not isolated. As the pair passed into its outer sphere of influence, analysts feared that even a slight mutual adjustment, one object pulling too hard on the other, could redirect their combined path, a path that was already projected to skim the magnetosphere. Engineers and orbital physicists at the Jet Propulsion Laboratory began rerunning simulations. New models introduced tidal opposition between the two objects as a variable, a completely new parameter in near-Earth object forecasting. The results were inconclusive. Some models showed the interaction would balance out, others showed a sudden mutual acceleration. One scenario predicted a rapid shedding of mass from one object, potentially flinging debris toward Earth's upper atmosphere. To the public, none of this was visible. Both objects remained small glints in the sky to amateur telescopes even as they approached. But in data rooms across the world, concern mounted. The tension between 3I Atlas and the Swan object was more than just a curiosity. It was now a factor that could affect Earth's near-space environment, and it was still growing. As the next observation window opened, a new pulse pattern emerged. It wasn't just gravitational. They were now influencing light too. The structures within both bodies were shifting subtly, as if preparing for something far beyond a simple flyby. Tidal forces, once background noise, had become a dominant variable in this encounter, and still, no one knew why. In the early hours after the twin objects crossed into the final orbital corridor near Earth, something began to change, not in a singular dramatic fashion, but in a series of scattered events, minor deviations, observational outliers, inconsistencies in data logs that began to point in one disturbing direction. The anomalies were no longer isolated, they were clustering. At first, these phenomena seemed disconnected. A minor magnetic deviation recorded by an amateur station in Iceland, a faint gravitational tug picked up by Lagrange-anchored sensors near Earth-Moon L1, a brief but unexplained photonic flare over Antarctica, dismissed initially as an atmospheric mirage. But when these data points were overlaid, their proximity, both in time and in space, revealed a coordinated shift. Agencies like NASA, ESA, and JAXA had already been operating under high alert protocols due to the unpredictable paths of 3I Atlas and the Swan object. But now, they were no longer just watching trajectories. They were monitoring the space between the objects, and more specifically, what that space began doing. The gravitational field maps generated every 12 hours began to show subtle distortions. Not strong enough to suggest an additional massive object, but oddly shaped, as if something non-physical, something spatial was being bent. These distortions weren't centered on the comets themselves, but between them, the region that had, up until now, been considered void. Then came the magnetotail bleed. The twin magnetotails of both 3I Atlas and Swan had maintained independent trails, each influenced by the solar wind, their motion, and their composition. But on December 26, their trails began to overlap. Not merge, not combine, but pulse in tandem. Two separate emissions, suddenly flickering at the same rate, like synchronized flares across millions of kilometers. Experts in plasma physics and heliophysics were brought into emergency video conferences. One working theory emerged. This was resonance, not of matter, but of interaction. That whatever lay between the two comets was either facilitating or forcing a shared frequency response. But it didn't stop at electromagnetic signatures. Infrared telescopes began to detect temperature spikes in microregions between the two objects. This shouldn't be possible. Space is a vacuum. Unless something was generating heat, or worse, absorbing it and re-emitting it in patterns. One researcher at the University of Tokyo coined a phrase in a now widely circulated internal memo: thermal lattices. He proposed that energy transfer was no longer being governed solely by solar radiation or kinetic energy, but by a medium, a structure, something invisible, possibly of dust or ionized matter, or something else entirely, stretching between the two bodies like filaments. The idea was dismissed by some, but not by everyone. ESA's Deep Field Radio Array in La Palma picked up something on December 27th, a consistent low-frequency hum centered not on 3I Atlas or Swan, but precisely halfway between them. It wasn't strong, but it was present. More importantly, it had never been there before. Suddenly, the notion of between was no longer academic. Something was occupying that space, or perhaps being formed in it. And that was the final signal scientists needed to change their vocabulary. They stopped calling them two separate objects. From this point onward, internal memos, mission updates, and risk assessments began referring to the phenomenon with a new term, the cluster, because what was once an encounter with two objects had now shifted into a dynamic system, and systems behave differently. Systems interact, evolve, and, sometimes, act with intent. And now, with just 72 hours remaining before the periapsis, the world was no longer watching two threats. It was watching one, and it had just begun to cluster. For nearly an hour, the Swan object had remained visually consistent, a muted glow characteristic of ice-rich bodies venting minimal material. But then, as Earth rotated into a more direct observational line, something changed. Without warning, telescopes in Chile, Australia, and Namibia began reporting a sharp increase in the object's reflectivity. The spike wasn't subtle. The Swan object suddenly began bouncing back far more solar radiation than before, almost doubling its apparent brightness in certain bands. And it wasn't due to proximity. Orbital models confirmed it was still over 150 million kilometers out. The increase in reflectivity was coming from the object itself. And that immediately raised questions. Typically, when a comet-like object experiences a reflectivity increase, it's due to the ejection of fresh volatiles, dust, ice, or gas expanding outward and forming a more reflective coma. But in this case, no such coma appeared. No plume, no tail. No expanded cloud of particles, just the core itself, glowing brighter, sharper, and more consistent than ever before. At first, some theorized that a solar flare might have ionized a layer of surface frost, causing a brief change in how the object scattered light. But the sun had been quiet during that observation window. The helioseismic and magnetic imager aboard NASA's Solar Dynamics Observatory detected no flare activity strong enough to explain what was being seen. Others proposed a surface shift. Perhaps the object rotated to expose a fresher, more reflective patch of ice or crystalline material. While this explanation made more sense, it conflicted with other data. There had been no change in its light curve, no observed rotation adjustment, no wobble. The object's spin, already extremely slow, remained steady. The more researchers looked, the less conventional the answers became. Then something subtle but significant occurred. Instruments that measured polarization, the way light scatters as it reflects off surfaces, detected a distinct shift. Before the spike, Swan's light was polarized in a pattern typical of dusty, porous ice. Scattered, diffused, non-uniform. But after the spike, the pattern changed dramatically. The light was now reflecting more uniformly, almost like it was coming off a smooth surface. The kind seen in metallics or structured crystals. That observation rocked the astronomy community. A transition from scattered organic polarization to coherent uniform reflection suggests the possibility of structure, or at least order, on the surface. In other words, something changed on the Swan object to make it behave less like a dusty snowball and more like a mirror. The next question was obvious. What could cause a change like that in deep space? Some speculated a surface layer of ice may have melted slightly under solar heating, then refrozen into a smooth crust. But again, thermal imaging showed no temperature increase. In fact, the object was cooling, not heating. Others considered electrostatic surface reorganization, where charged particles from the solar wind could rearrange fine dust into smoother patterns. But that would require a much higher voltage than what the Swan object seemed to be experiencing. Then came a hypothesis that made headlines, though many dismissed it immediately. What if the reflectivity change was not natural? What if it was a surface coating, applied, shifted, or revealed? The idea that something was intentionally altering its albedo, whether through mechanical rotation, vapor deposition, or embedded material, was immediately categorized as fringe. But it was hard to ignore the perfect timing. The increase in brightness aligned precisely with Earth's most favorable viewing angle, as if the object had planned its own unveiling. For now, the truth remains hidden in the light. But the implications are spreading fast, because whatever caused the Swan object's surface to suddenly gleam, it was not a simple outgassing event, and it might not be simple at all. For centuries, cometary science has thrived on observation, simulation, and the iterative refinement of models. When a comet enters the inner solar system, we expect a predictable evolution: sublimation of volatile ices, formation of a coma, an ejection of dust and gas along well-defined jets, often aligned with solar radiation and spin vectors. These behaviours have been catalogued across dozens of missions and telescopic studies. From Halley's unpredictable burst to 67P's bilobed core, every anomaly has eventually found some place within our models, even if loosely. But 3I Atlas has once again placed itself outside the boundaries. In its most recent high-resolution composite taken jointly by the Solar Orbiter and Earth-based interferometric arrays, the structural composition around the object's nucleus defies all known configurations. What was first dismissed as noise or data artifact has now been confirmed across multiple instruments and angles of detection. The central issue is symmetry, a symmetry that shouldn't exist in a naturally eroding celestial object. Rather than chaotic outgassing vents or fragmented jets randomly spraying material, the emissions from 3I Atlas form a lattice, a web-like alignment of dust streams, filamentous in nature, emanating from fixed nodes on the comet's equator and poles. These nodes appear to remain stationary even as the object rotates, a behaviour that violates Newtonian expectations for a loosely bound ice rock structure tumbling through solar winds. Researchers at JPL's Advanced Morphology Unit compared the observed structure to every previously catalogued comet, including historical anomalies like Comet Lovejoy, Ison and Shoemaker-Levy 9. None of them exhibited even partial alignment with what's being observed around 3I Atlas. At first, scientists believed this symmetry could be explained by rotational harmonics, perhaps an internal axis tilt synchronized with its orbital inclination. But this explanation collapsed under the weight of observational consistency. The alignment is too perfect and too stable. It doesn't precess. It doesn't drift. And most puzzling, it reacts to solar flux with precision timing, as if it were aware of its energy intake. Dr. Lee Hara at the University of Tokyo proposed that the structure may be held together by a magnetic scaffold, not a solid surface architecture, but an invisible exoskeleton made of charged particles, locked in place by induced fields. That alone would be groundbreaking, suggesting a level of plasma field manipulation unknown in natural bodies. But even that theory faces a daunting obstacle. Where is the power source? No known comet generates enough internal energy to maintain that kind of coherence, and if it's not electromagnetic, then what is it? Infrared backscatter from the James Webb Space Telescope added another bizarre detail. The structural web appears to pulse, not constantly but at irregular intervals, and only when in alignment with Earth's position in the heliospheric current sheet. Some researchers quietly wonder if this pulse is more than thermal discharge. If it could, in some still unexplained way, be a signal. Others are more conservative. They caution against anthropomorphizing natural behavior, against projecting meaning where there might only be misunderstood physics. But even they admit, off the record, that this is unlike anything they've ever seen. The ESA's Gaia team submitted a cautionary abstract to the International Astronomical Union, suggesting that if the structure is indeed synthetic or quasi-synthetic, we must begin contingency discussions about contact protocols, or at the very least close pass preparations. While that abstract has yet to be formally accepted, the very existence of such a document is telling. So far, the structure doesn't appear aggressive. It doesn't maneuver or alter trajectory in relation to Earth or our observation arrays. But it doesn't behave randomly either, and in celestial mechanics, deliberate behavior is not something we attribute to comets. Yet here it is. Spinning, pulsing, symmetrical, and in all our databases, in all our telescope archives, in centuries of comet modelling, there's nothing quite like this. The solar wind is not just a gentle stream of charged particles, it's a relentless force. Flowing from the sun in all directions at speeds ranging from 300 to 800 kilometers per second, it shapes the behavior of every comet and interstellar object that crosses its path. Tails form in response to this invisible pressure, always pushed outward, always aligned with the direction of solar radiation. That's the rule. But this time, something broke it. As observers focused their attention on the R2 Swan object during its accelerated motion near the outer Earth-Mars corridor, a quiet anomaly took shape. Ground-based telescopes first noticed a change in orientation in the object's dust tail. Then came confirmation from heliospheric imaging instruments on NASA's Stereo-A probe. The tail wasn't being pushed with the solar wind anymore, it was curling against it. That observation, though visually subtle, was momentous. It suggested that some internal force, something stronger than the steady pressure of solar radiation, was actively dictating the motion of the swan tail. Not only that, but the tail's change was not uniform. It rippled. It bent with precision in certain arcs while holding firm in others. It exhibited something that space physicists rarely ever assign to passive material: structure. This wasn't a random disruption caused by a solar flare or magnetic interference. There were no active coronal mass ejections during this interval. Solar conditions were considered moderate. No major radiation events were reported by SOHO, ACE, or any Earth-orbiting monitors. In other words, there was no external factor that could justify what was happening. It had to be internal. The idea of a tail moving against solar wind pressures violates one of the foundational expectations in solar system dynamics. A comet in its natural form is not equipped to resist or redirect the solar wind. It's composed of frozen gases, dust and rock, materials too light, too fragile, too passive to alter direction independently. So when the R2 Swan object displayed such behavior, two interpretations emerged. The first was mechanical. Perhaps the object was spinning in a new way, exposing asymmetrical outgassing jets that were powerful enough to redirect material. That's possible, but it would require both an extremely specific axis of rotation and a level of internal pressure never before seen in a natural comet. No comet on record has produced such a high degree of jet asymmetry that it could counteract the solar wind's vector over such a large surface area. The second explanation was less comfortable: that an unknown, perhaps artificial mechanism was influencing the ejection of material, something with the ability to control the flow direction of released ions and dust, something capable of deliberately shaping the tail, not for the sake of chaos but for structure. This theory gained more weight when scientists noticed another clue: a sudden spike in ionized sodium and carbon emission lines within the tail, recorded by a spectrograph in Chile. These elements can be present in comets, but they do not appear in strong emission unless specifically agitated or exposed to high-energy interactions. The timing aligned exactly with the tail's shift. The implications of that are not just scientific, they're philosophical. Because a tail that defies the sun is not just a feature, it's a message. Something pushing back against a known universal force suggests either active resistance or intention. And if R2 Swan is acting with intention, the conversation about what it is changes entirely. For now, the tail is stabilized into a new formation, shaped like a slight wave that bends backward toward the object's leading edge. It's as if the tail wants to follow, not flee, like it's connected to more than just dust and particles. Something unseen may be writing its shape, and Earth is right in its path. The cloud was always there, drifting loosely around 3i Atlas like the remnants of some long-forgotten collision. From a distance, it looked like any typical coma, a loose halo of ejected particles, the sort of thing you'd expect from a volatile interstellar object interacting with sunlight. But as the twin comets, 3i Atlas and the Swan object, continued their journey, observers across the globe began noticing something they couldn't explain. The dust cloud was behaving strangely, not expanding, as most cometary comas do, not thinning, not fading, but compressing. Images captured by NASA's Solar Terrestrial Relations Observatory, STEREO, and cross-checked against Japanese Hinode satellite feeds confirmed it. The envelope of dust was drawing inward. Telescopes that previously captured the cloud as a fuzzy bloom were now recording tighter formations. Astronomers measured the radial density of the particles and realized the compression wasn't subtle, it was dramatic. Within hours, regions that had previously shown low reflectivity were suddenly denser, more concentrated, even darker. It was as if the cloud was being pulled inward by a force originating from the core. Some speculated this was simply a gravitational effect, a result of internal mass shifting inside the object. But that didn't make sense. Cometary dust doesn't respond this quickly to subtle changes in gravity. And even more perplexing, the particles weren't just collapsing toward the nucleus, they were forming patterns, hexagonal lines, radial filaments, rings that didn't behave like standard magnetic waveforms. The European Space Agency's Solar Orbiter team ran particle simulation models through their high-speed render farm in Darmstadt. They tried to match the compression patterns to known behaviours: dust collapse due to magnetic reconnection, thermal pressure gradients, even exotic material behaviour. Nothing fit. It was then that a paper quietly circulated among astrophysicists in Geneva, Singapore and Pasadena. What if the dust envelope wasn't collapsing due to physics alone? What if it was being manipulated? The suggestion was wild, but so were the visuals. A new infrared sweep by the Spitzer Legacy Archive showed consistent heat signals aligning with the compressed structures, signals that seemed too uniform for natural processes. Instead of random, chaotic collapse, the dust appeared to be aligning itself like iron filings under a shifting magnetic field, and the motion was coordinated. Dust filaments twisted gently, coiled like rope around invisible spindles, and then locked into place. From 1 hour to the next, a ring would form, tighten, then vanish into the nucleus, as though the material was being absorbed or structured into something internal, something we couldn't yet see. That triggered another wave of panic. If this wasn't a breakdown, but a build-up, what was being assembled? Astronomers had no real answer. The closest analogues came from laboratory experiments on magnetic confinement of charged particles, like the rings generated in experimental fusion reactors. But comets don't build reactors. They don't engineer magnetic fields, and they certainly don't assemble coherent patterns from their own debris, unless they weren't just comets anymore. By the time this theory was whispered across Slack channels in NASA's Goddard facility, the language had already changed. Analysts no longer referred to dust compression or coma reconfiguration. Internally, they had adopted a new, unofficial term: structure formation. It wasn't just material collapsing, it was material behaving as though it had intent, and as the envelope compressed tighter still, forming a dense, shimmering shell around 3I Atlas, the next question was no longer how it formed, but when it would open. Because anything that builds eventually activates. And 3I Atlas was compressing faster than anyone had expected. High above the poles, long before the public noticed, the auroras began behaving oddly. At first it was subtle. In satellite imagery, thin streaks of ionized light bent in ways that didn't align with normal geomagnetic flow. The colours extended beyond typical green and red into deeper hues of violet, turquoise, and even rare UV flares not usually visible to the naked eye. The shapes, too, normally graceful, flowing curtains of light, began to fragment. They now flickered into repeating arcs and symmetrical whorls, almost like symbols. Initially, it was dismissed as atmospheric interference. The Earth had just endured the electromagnetic pressure from 3I Atlas's passage, after all. Scientists proposed plausible explanations: residual charge alignment, localized magnetic turbulence, or aftershocks in the solar wind. But those theories collapsed when the same pattern began forming, again and again, across both poles, in perfect synchronization. This wasn't a natural disruption, it was structured. Multiple observatories, including the South Pole Station and the Kiruna Geophysical Observatory in Sweden, started logging repeating timestamps. These auroras pulsed with timing accuracy down to the millisecond. In some areas, the colours aligned into mirrored formations, matching what appeared in the opposite hemisphere. In others, the magnetic wavefronts formed loops, crossing over into regions they normally couldn't reach due to the Earth's dipole boundaries. It was as if something was resonating with the planet's magnetic field and using it like an antenna. Dr. Naoko Sato, a plasma physicist working out of Kyoto, described what she saw during a live feed from the Themis satellite array. "They're not just auroras," she said, "they're modulation waves. The ionosphere is being sculpted, patterned. Something is embedding information into the sky." NASA and ESA downplayed it. A new joint memo labelled the event as a post-storm ionospheric response anomaly, but they offered no math. No model, no timeline for recovery. And the auroras kept coming. Even during periods of geomagnetic calm, the patterns reappeared. always near midnight, always centered on the poles, always with the same rhythmic cycle. Theorists started mapping the frequencies. Amateur radio operators in Iceland, New Zealand, and northern Canada all reported bizarre distortions in VLF transmissions. Long-wave communications, normally stable in those latitudes, would drop out completely during the aurora cycle. Then, just as suddenly, they would return, but with harmonic overlays. It was as if something was echoing through the signals, layered tones that carried no voice, no pattern, just presence. By the third night, new claims emerged. Several independent researchers, analysing the auroral frequencies, reported embedded numerical primes, sequences of numbers only divisible by themselves and 1, interspersed at regular intervals. They weren't sure how the primes were forming, or whether they were natural, but their presence couldn't be dismissed. In pure mathematics, prime sequences don't just appear randomly in electromagnetic fields. Something had to generate them. Back at the South Pole, the aurora had shifted again, now forming concentric rings that rotated in opposite directions. The outer rings pulsed inward, the inner ones pulsed out. It created a visual interference pattern that no known natural process could produce. One researcher compared it to a binary encoder, translating physical motion into possible data. And yet the official channels remained silent. In the silence, speculation grew. Some said 3i Atlas was broadcasting, still sending information using Earth's own magnetosphere as a medium. Others believed the aurora was a defense mechanism, Earth's magnetic shield adapting to a foreign presence. A few went further, suggesting it was a reply, that something beneath the crust, something ancient and dormant, was finally waking up to respond. But no one could say for certain, because all we had was light, colours in the sky, patterns that didn't belong, and a sense that someone, or something, was speaking in a language Earth hadn't heard in thousands of years, and it had chosen the aurora to do it. When the solar wind hits Earth's magnetic field, the response is typically predictable. A compression on the sun-facing side, an elongation on the night side, and a ripple effect that causes auroras, radio disruptions, or occasionally even transformer failures. Scientists have spent decades modelling these interactions, especially during solar storms, CMEs, or close approaches of charged objects. But the reaction from Earth's magnetic field in the presence of 3i Atlas and the approaching Swan object did not follow any standard protocol. Instead of a symmetrical compression, sensors aboard the Magnetospheric Multiscale Mission, MMS, began reporting something very different. Between 4:42 am and 5:01 am UTC, the magnetic field began to twist, not collapse or bend under pressure, but rotate subtly, like it was being redirected or refracted by something unseen. This wasn't just a local phenomenon. From satellites over Brazil to stations in northern Canada, geomagnetic monitoring equipment all picked up the same anomaly. The twist appeared to originate above the equatorial zone, slightly ahead of Earth's orbital path, then spiraled outward, like a helical ribbon unwinding in slow motion. This behaviour baffled analysts. Under typical conditions, such a pattern might hint at a polar shift or a geomagnetic anomaly caused by deep Earth processes, but those are slow events, unfolding over decades or centuries. This was happening in real time, and it was tied directly to the spatial positioning of the incoming objects. At first, the theory was interference. Perhaps the instruments were responding to unrelated plasma turbulence. But when teams cross-referenced this with solar data, it became clear there was no CME at that moment. The sun was quiet. The particles were flowing in from space, but not in the chaotic high-energy bursts typical of a solar event. Instead, these were low-velocity ions with a very precise trajectory, as if guided. That's when one term began appearing in internal ESA and NASA documentation: magnetotail threading. The magnetotail, Earth's long magnetic extension facing away from the sun, usually sways and flutters like a windsock. But now, for the first time in over a decade, high-resolution magnetic field lines captured a rare event, a threading pattern where two external fields attempted to pass through and align within our own. It was as if Earth's magnetic field was being partially woven into a second structure, a foreign structure, a double helix of magnetism. Speculation surged. Could this be Swan? Was the object dragging a long tail of magnetic plasma? Or was it something even more complex? A coordinated effect between 3i Atlas and Swan, like two poles of an invisible magnetic net adjusting their angles. At ground level, most people felt nothing. A few amateur radio operators noticed that HF frequencies briefly faded, even though solar weather apps showed quiet conditions. But the real concern was not in the moment, it was in the pattern. Because after the twist, the field did not return to its original state. There was a persistent offset, a half-degree drift, small enough to be written off as background noise, large enough to be seen by anyone who was really looking. And one observatory in Antarctica was. The Amundsen-Scott Station's geomagnetic team logged a second disturbance 22 minutes after the first, this time centred at a depth of nearly 300 kilometres beneath the surface, beneath the magnetic poles themselves. This wasn't just a brush-by event. Something had threaded Earth's magnetosphere and left behind a fingerprint, and the pattern matched nothing we've ever seen, not solar, not interstellar, not natural. And with the object still closing in, this was just the beginning. It wasn't supposed to shift again. After hours of continuous observation, most analysts had assumed that the object trailing behind 3i Atlas had settled into a stable orbit. The initial patterns, erratic, almost chaotic, had slowly transformed into what seemed like predictable alignment. But just after 4:12 a.m. UTC, a new series of data streams hit the Space Situational Awareness servers. Something changed, and this time it wasn't just a drift. The shift was directional. Instead of continuing along its projected arc, the trailing object, previously referred to as an unclassified fragment, began adjusting its orientation, not drifting due to gravity, not pushed by solar radiation, but rotating and realigning itself in short, deliberate intervals. Observatories tracking its telemetry described the movement as stair-stepping, a pattern where the object locked into a position, held steady for exactly 91 seconds, then pivoted, always at the same angle, and locked again. The repeated angle of these movements wasn't random either. Each successive shift appeared to point back toward Earth. That realization sent a shockwave through international monitoring stations. What was once assumed to be a passive fragment, debris or a natural satellite ejected from 3i Atlas, was now behaving as if it had targeting capacity. Not propulsion, but orientation, as if it were trying to maintain a lock on a single point across hundreds of thousands of kilometers of space, and that point was moving with Earth's rotation. More data followed. Leader reflection tests from ground-based transmitters revealed something unnerving. The object's outer surface had changed reflectivity again. It was no longer uniform. Instead, it displayed banding, layers of material that absorbed some frequencies and scattered others. Infrared mapping began showing a faint heat gradient along the object's edges. This gradient appeared to intensify slightly during each 91-second interval. The implication, either internal activity or energy absorption and re-radiation. In short, it was interacting with light and possibly building charge. This pattern drew the attention of defense analysts, especially those familiar with kinetic interception systems. A structure that orients in precise intervals and absorbs ambient energy might not be passive. It could be observational, or worse, preparatory. Not in an aggressive sense necessarily, but preparatory in the way a sensor array would behave before relaying data. Before activating, speculation ran wild. Was this some kind of autonomous scout mechanism released by 3i Atlas? A dormant sensor? Or something left behind intentionally, not as waste, but as a beacon? Theories emerged suggesting that this final shift was a form of signalling, not to us, but to other objects. A relay of location perhaps, or an echo to measure distance. But the one thing no analyst could ignore was the synchronization. Every movement, every interval, every radiative emission cycle. They all lined up perfectly with Earth's orbital curve and rotational speed. The trailing object wasn't just reacting to Earth's presence, it was locked to it, not by gravity, not by inertia, but by some kind of pre-coded behavior, a guidance system without engines. NASA and ESA maintained silence. Only a quiet update on their public orbital elements page showed the new telemetry arc. The object had a new designation, Object Luma 7, a code not previously used in any known tracking system. The label hinted at artificial classification, not just a rock with coordinates, but something potentially significant enough to isolate from standard debris catalogues. For now, it continues to rotate, every 91 seconds, always realigning, always keeping watch. What it's watching for remains unknown. As Earth slowly spins through the dark vacuum of space, it does so now under a silent clock, a countdown not measured in calendar days or digital timers, but in the strange rhythms of celestial events that none of us fully understand. The moment 3i Atlas passed our planet, everything technically returned to normal. The skies quieted. The sensors, once spiking with interference and anomalies, began stabilizing, and yet, something doesn't feel finished. Across observatories, from Chile's desert plateaus to Antarctica's icy domes, researchers are continuing to monitor what Atlas and the Swan object left behind. They're not just watching where the comet goes next, they're observing what it might have activated. Instruments designed to detect cosmic dust now report increased particulate activity in Earth's thermosphere. Low-frequency antennae are picking up signal patterns that resemble magnetospheric distortions, but with no solar storm in sight, it's as if something was planted in our near-space environment, something that's still interacting with our magnetic field. Meanwhile, atmospheric models are being revised, not because of climate change, but because of new thermal inputs in the upper layers. In the days following the Atlas-Swan convergence near Earth, temperature sensors on sounding rockets and high-altitude balloons recorded anomalies, pockets of localized heat where none should exist, an energy signature that seems to ripple out instead of fade. We often think of comets as remnants, icy time capsules that offer glimpses of the early solar system. But what happens when a comet behaves more like a catalyst, a trigger? What if these objects aren't just wandering debris but instruments themselves? Not necessarily artificial, but active, charged with a purpose we don't yet have the framework to comprehend. The possibility alone reshapes everything. If Atlas activated the Swan object or vice versa, then we're no longer dealing with isolated anomalies. We're witnessing a sequence, an interaction, a message perhaps, if not for us, then for something else. And if space isn't just random but contains timed mechanisms, then Earth's proximity to these cosmic exchanges is no longer coincidence. It's part of the chain. The silence that follows such revelations is not empty. It's filled with implications, conversations in quiet laboratories, eyes that linger longer on telescopic feeds, engineers sketching theoretical interceptors, writers and thinkers asking what if we were warned, or worse, what if we were simply seen? It's too soon to say what will come next. The trajectory of 3i Atlas still leads toward the inner solar system, with adjustments that continue to confuse orbital models. The Swan object, now dimmer, appears to be trailing it, but at a controlled distance. The idea of one comet guiding or controlling another would have sounded absurd just a few weeks ago. Now it's written in the logs of NASA, ESA, and amateur forums alike. So we watch, we listen, and for the first time in a long time we prepare, not for collision, but for comprehension. If you've made it this far into the video, thank you for joining us on this journey. We encourage you to subscribe, leave a comment telling us where you're watching from, and share this episode with someone curious about the hidden patterns of our universe. Because something is unfolding, and we don't want to miss it. Not when the sky itself has started speaking, and not when what it's saying might change everything.